AI models are getting bigger. It can take thousands of accelerators to pre-train one. While most people won't get to pre-train a large model, I expect that quite a few are going to try to post-train a model using RL. And this could take a significant fraction of the compute needed for pre-training. And even more people are going to try to serve large models. For example, DeepSeek V4 runs well on 16 GPUs, which means like 2 or 4 hosts. So we're moving into multi-host inference and training. There seems to be this feedback loop where larger models work better, so hardware vendors are connecting more and more accelerators with a fast network fabric like NVLink, TPUs use ICI, InfiniBand. Most multi-host training inference is moving out of the largest AI shops and becoming relevant to more organizations. And those organizations are, of course, using Kubernetes. Out of the box, Kubernetes has good support for what I would call single-host AI workloads. It handles them the same way as it does traditional workloads like jobs and deployments. In a typical Kubernetes cluster, pods from different workloads are bin packed onto nodes, and the pods that form a single workload, they usually have no or little peer-to-peer communication over the cluster network. When a new pod shows up, the scheduler's job is to try each node until it finds a place where it fits. This process then is repeated individually for each pod in the workload. With multi-host AI workloads, several things change. The accelerators are now connected with these fast network fabrics that span groups of hosts, but not necessarily all the hosts in the cluster. Again, this is NVLink, ICI, InfiniBand. In this example, there's 2 fabrics, and each fabric has 4 nodes. And then on the top fabric, there's like 3 is not a normal number, but for this example, there's 3 pods. A more common, more realistic would be have 18 hosts or 64 hosts in a group. When a new multi-host AI workload shows up, the scheduler needs to take the whole group of pods, in this example 2, and needs to try to match that separately against each group of nodes. So first group of 4, no fit. In summary, as models have grown, workloads have grown too, hardware has changed, so scheduling needed to change too. Instead of matching one pod to one node and then repeating that process, you have to match several pods to groups of nodes, and you want to do that kind of in a single pass or action. So how does Kubernetes support multi-host AI workloads today? Some pioneering users kind of took advantage of Kubernetes superpower, which is extensibility, which is designed in from the beginning to Kubernetes. They use 2 different types of extension points. One is that you can design new workload controllers, and they took advantage of the fact that you can replace the default scheduler, or you can layer over it and you kind of use it as a pass-through. The community has been creating custom workload controllers since 2016. But job set and leader worker set are examples that were specifically designed for multi-host inference and for multi-host training. I got that backwards, not respectively, but the other way around. These are some examples. There are other ones. The Kubeflow project's working on the same type of thing. The second thing that happened was they were adding these alternative schedulers. They're replacing or extending the default scheduler, kube-scheduler. Kueue and Volcano are probably the 2 best known options, I would say, but there's several others that also support enough of this topology awareness to handle multi-host workloads. We think it's great that Kubernetes is extensible enough that people can bring their own schedulers. There's this innovation. They can move much faster than our release cycle. There's less kind of need to build consensus. So that innovation is great. This is not something that we want to change. And I want to make sure you take that away from this talk. We want these alternative schedulers to keep working. We don't want to break them or force them to change. And we want these projects to keep innovating. That's super good for the community. However, a year ago, Wojciech and I kind of looked at the overall situation and asked, is this really the optimal state for the community and the good final state once this multi-host space kind of simmers down and standardizes a little bit? And so we looked at both these types of extension mechanisms separately. So for workload extensibility, we felt that was working pretty well. It's letting Kubernetes evolve rapidly. I observed, for example, the job set and leader worker set projects that I'm most familiar with. Those were moving really quickly, and we did not want to slow that down. I think workload extensibility has worked so well over the years. It's really helped Kubernetes expand the addition of stateful workloads, database operators. It really let Kubernetes expand and continue to be like the one system to manage all of your compute. But I guess there's so many of these that like no one can keep track of them all. Like we vaguely have some monitoring that tells us that there's lots of different customer sources installed by users in our cloud. I've searched GitHub. You can find there's a lot of customer sources. Not all of them are obviously for AI training, multi-host, but the scheduler needs to work with every type of resource. It's not really reasonable for the scheduler to like take a dependency on listing and watching every type of resource and try to interpret its specs. So that was kind of one area that could use improvement. And then when we looked at scheduler extensibility and replacement, we saw a number of things that we didn't know if we liked as like a long-term situation. First, we saw that people are, when you spin up a new Kubernetes cluster on a cloud provider or like use a stock Kubernetes release, there's really pretty limited support for multi-host out of the box. Setting up an alternative scheduler, some of the instructions are pretty good. It's still extra steps, which could be a little discouraging for someone coming new to this space. But let's say you choose one and you install one. Next thing you want to do is like, let me go find some examples. Well, with like 5 or more different options, they each have different, labels or APIs they use to configure scheduling. So now you got to find an example to get started that is relevant to your scheduler. So that's kind of fragmenting the community's effort at like standardizing patterns, charts. We also didn't love that a lot of these APIs were based on labels. It's kind of a thing with Kubernetes contributors, like we like validation. And another problem we saw was that these new fabrics, like some of them need configuration. Probably the most well-known is like compute domain. People have heard of that from NVIDIA. And we just think that there's going to be increasing need to do fabric reconfiguration in conjunction with this. And the DLA project was like moving along really quickly, but because they're really focused in core and these extensions are out of core, there wasn't like a strong testing or like SIG reason for these things to come together. So it wasn't coming together perfectly. And the last thing was that while some of these schedulers do support running long-running workloads, like you would tend to do for inference, you kind of want to have the same patterns as a deployment. It's not what they're first designed for. And so I don't know if this is going to happen, but we're hopeful that we can have one scheduler that can really mix long-running and batch workloads and just be amazing. So based on that, we kind of draw some conclusions about like what's needed in the core project. We started working towards these goals. And this is, first is that pods need to be able to specify what group they're in. We need a core type to represent those groups of pods. It can't just be a label selector. And we wanted to try to do gang scheduling as an intermediate step. It's not quite full topology, but it's a good step we could get to in 135. So looking at these new changes, you have a pod. A pod says what workload it's part of. It says if it's part of a pod group. Those reference this new object, which is also a container to show where you can hold policy. And we only have one policy for the scheduler right now. It's called min count, and it says this is how many nodes are going to be in my gang. But we expect that over time, we have ideas on lots of different policies that can go in this workload container. So we're not expecting users to edit their pods or their pod templates or make these workload objects. We expect that relevant controllers like job set, leader, worker set, job are going to manage these for you behind the scenes, inject the values into pods. It should just work. So let's see how this works inside the scheduler. When the scheduler sees a pod that's got a spec'd out workload and there's a min count, it's not going to let the pod go through the pipeline immediately. It's going to wait until it sees all three. And then in 135, just going to let them go through one at a time. And then they're going to get stuck. They're not going to be able to go to binding phase yet. And then when all three find a place, then it's going to release them and let them get bound. If something happens, if there's not enough resources, they're going to get kicked back and they're going to wait again. So that's what we've completed in 135, but there's a lot more that we want to do.
Okay, thank you, Eric. So I'm going to talk a little bit now more on what we are planning to do next. So The first step that Eric just described for like gang scheduling is preventing us from starting part of the gang where we know that we can't schedule the rest of it. This is great, but this is actually not enough. Like imagine a use case where all pods need to run in the same zone or in the same NVLink domain. Then if we schedule pod by pod, then the placement decision for the first pod is actually determining the topology where the rest of the pods will also land. So, and it may actually make the workload as a whole unschedulable. So to make optimal decisions, we actually need to think globally, and we need to take the whole workload into account. And this is exactly what we are planning to do for 136. We want to introduce a new phase in scheduler framework that will let us to find the placement for the whole group of pods in one shot effectively. And as a result for it, at the end of this phase, we want all the pods from that workload have a proposed placement, or we call it like nomination. So we know where we would like them to, we know where we would like them to be placed. So as a next step, they will be going through the existing scheduling phases, and this will be pretty cheap because we already know where we want to run them, and we are treating it more as a validation. So validation step. So if the state didn't change, like it should basically always succeed. So once all the pods like went through those phases, they again block like the same way before binding, and they are now ready for binding. And we don't have enough time today to like dig deeper into like all the things that we are planning. So I will just signal that we are also planning to make binding a little bit more sophisticated. So with multiple pods, with the whole workload, like binding is no longer atomic. So it's possible that like it can fail later in the cycle, later for one of the pods because allocation of DRI device fails or like kubelet rejected it. So we need to be able to recover from that situation. So we want to make the binding more multi-step process that will help us to potentially recover from those failures that can happen. Okay, so let's now assume that like all of this happened, and unfortunately, this is still not enough. Like in majority of cases, we not only care about like all the pods to be scheduled together, we actually need them to be running together for the whole time. So and there are many use cases where like all the pods needs to run at the same time in order for the workload to make progress. This is the case for AI training. This is the case for like multi-host inference, and like there are many other use cases. So if any single pod of those workloads is not running, the workload as a whole is effectively stalled. And this is something that we need to improve in Kubernetes. So we want to introduce this concept of like runtime gang or the behavior. So addressing that like consists like of two primary areas. Like first is like workload-aware preemption. So when scheduler needs to preempt some of the pods, it can't really anymore look into individual pods that it will preempt. It needs to take into account the effect of that preemption of that pod on the whole workload. So like preempting a single pod may actually make a huge workload potentially unusable and stalled because of that. So this is another thing that we would like to push to alpha in 136. But preemption is not the only reason for disruption. There can be like machine failure, there can be any other disruptions. And so basically we need an ability to, in those cases, to reschedule that workload. So find a new placement for it where it can continue its work. And so rescheduling, the workload-aware rescheduling is basically the other area. And you can think about it as effectively as scheduling, but with the context of like current placement of the workload. Okay, so let's now slightly change the topic and let's talk about performance of the workloads. So AI workloads are often like extremely chatty, so their performance like highly depends on the performance of the physical network underneath. And as Eric mentioned already, like the underlying infrastructure, like it's no longer like flat. It's not a flat network. So depending how exactly we place the individual instances of our workload, the performance may drastically differ. And we are not talking about like single-digit % differences. We are often talking about like very, very substantial difference in performance. So simplifying a little bit, like we can say that the infrastructure itself forms a forest, and the closer to the leaf you are, like the better performance, or the closer to the leaves they are, like your the lowest common ancestor of your instances is, like the better performance you are. It's obviously a simplification, but it's like probably good enough for the sake of this presentation. So to better illustrate that, let's take a look into an example. So we have a workload that consists of like 2 pod groups, and to achieve its optimal performance, each of those groups need to run in a single sub-block. But together, like all those groups need to run in the single block. So what we need to do to like satisfy those requirements, we first need to allow for like expressing those constraints at the API level. And second, we need to obviously adjust the scheduling algorithm and make it topology-aware. So make it both understand the topology, but also be able to satisfy those requirements. And this is another thing that we are like very actively discussing and working on, and we would like to have it in alpha in 1.36 too. So this is coming too. So okay, so we touched like multiple different topics, but there are all kind of part of like a wider category of what we call like workload-aware scheduling. But this is only like this is only one of the work streams of the scheduling evolution that we believe are important to address. If you look at the scheduling like a little bit more holistically. So in the rest of the presentation, I'm going to like super briefly touch on the other 2 work streams. The second one is the tighter integration with like infrastructure autoscaling. Historically, we were thinking about like infrastructure autoscaling as a like kind of separate thing. And it's how like cluster autoscaler and Carpenter operate. Like scheduler is not really aware of their existence. But in fact, like infrastructure autoscaling is nothing else than scheduling, but just on not yet existing infrastructure. So it's, and obviously like provisioning that capacity if it needs to, but in the end, it's like a scheduling. And the third category is effectively providing a better building blocks for scheduling extensibility. So as Eric already mentioned, like this is super important. Like we will never try to address like all the sophisticated scheduling features in core, like the need for all those orchestrators for Kueue, for any other schedulers, third party, will always be there. Like there will always be features that will be implemented by those and will not like be included in the core. So ensuring that this integration can work correctly is like super important for us. So so this slide shows like our current thinking about the high-level architecture of the system. I'm sure it will evolve over time. It actually evolved visibly since like we first created it, like I don't know, half a year ago or something. But during the rest of the presentation, I'm going to focus a little bit on the left part, so the infrastructure autoscaling and integration with scheduling, and the top part, which is like the third-party or like ecosystem orchestrators and schedulers. So let's start with the infrastructure autoscaling. So how it currently works is basically it provisions a capacity based on simulations that it is doing. So it needs to, like any infrastructure autoscaler, needs to perform certain like scheduling simulations to see if the workloads or pods that are currently pending will actually fit into the capacity that it's trying or can consume the capacity that it wants to create. But scheduler actually is completely ignoring any of those. And it can result in like potentially suboptimal decisions that it makes later because, for example, it only observed part of the provisioned capacity so far. So like it can make potentially very different decisions. And as I already mentioned, like making optimal decisions actually requires thinking globally. So the potential capacity is actually equally valid option to consider for scheduling. So the not yet existing capacity may actually be the best option for your workload because it potentially can be more performant on that different type of infrastructure, or it can be run cheaper. So we need to take that into account. So to allow that, we are actually discussing a high-level design where we introduce a new like potential capacity API, which allows scheduler to learn about what kind of infrastructure can be provisioned in the cluster. Then based on that, scheduler can take that into account when making the scheduling decisions and potentially request for provisioning that certain types or certain kinds of like nodes or devices. And then it can also learn about like the capacity that is currently being provisioned and should soon appear. And only like in that kind of model, like we can put all the scheduling-oriented logic in a single place and allow for this like thinking globally about all the potential options. Okay, so let's move on to the last one. The extensibility work stream, like it consists of like two areas, like the first being the integration with workload orchestrators like Kueue. And in order to decide which workloads like an orchestrator would like to run, so in case of Kueue, which workloads should be admitted, which should be still queued, like it needs to be able to run many different or simulate many different scenarios to choose the best option. And to address it, we would like to expose the simulation API. So it will effectively be a mechanism for simulating scheduling decisions without the need to committing to actuating the decision if it can succeed, or even creating the pods themselves. So in other words, like it will allow to answer the question, like, can this workload or this set of workloads be scheduled? And if so, like, what will be the side effects of it? So like what preemptions will happen, what additional capacity needs to be provisioned, etc. So unfortunately, there are still like many open questions here before we expose the API. So as a more shorter term mitigation or like help to help for those orchestrators, we would like to create a library that will allow or simplify running those simulations in memory for those components. But the API remains the North Star here. And the second sub-area is like extensibility for like third-party schedulers. It will always like remain a valid use case because I can always have like requirements that kube-scheduler can't satisfy or can't really can satisfy, or are even impossible to like be expressed in the API. So the extensibility is super important here, and we believe that there is like a missing primitive here. We tentatively call it like a reservation, but it's probably not the best name. But the mechanism behind that is something that will allow us to obtain a specific set of resources and manage them like yourself. So as an external scheduler, I can ask for a specific set of resources, and once granted, I can like arbitrarily use them to schedule whatever and however I want on that, and without being afraid that someone will steal them from me, or like someone will try to race with me for like those being used. And it's probably worth mentioning that like this mechanism will allow us to also address like multiple other like use cases, where, for example, ensuring that my workload has enough resources to run during upgrades, and those will not be like taken in the meantime by some other workload. Or I have a pipeline of workloads and I would like to reserve resources for them, or I would like to block resources for maintenance. This is another thing that we are like thinking about, though probably not for 130 6 yet, given how many other things we would like to push. And I think that's pretty much it, what we have for today. As you can see, we are still pretty early in the process with any of those. So if you have any feedback, please don't hesitate to reaching out to us. If you see any requirements that may not be, if you have any requirements that may not be met by those, definitely let us know. If you have better ideas how those can be solved, we are definitely open for any kind of feedback. We will be with Eric and Dominic. There are other folks from SIG scheduling here too. So we are definitely happy to chat either after this presentation or later offline or on GVC. And I think that's all. So thank you very much. And I think we still have a little bit of time for questions.
Go ahead. So the topology-aware scheduling problem that you have there is about placing different workloads close together. Have you considered whether there's a use case for the opposite? Because if the tree that you're looking at represents failure points, spreading them apart may also be something that's useful.
So yes, I think we definitely want to do. I think it's there are some simple mechanisms that they are not enough, pod anti-affinity that allows you to achieve some of that. We definitely want to consider anti-locating, or however we will call it, as a thing that we want to do, but it's not on the top of the list. I think that the collocation is much more important use case for many of our users. So
I did my PhD thesis on the opposite problem, so we should talk.
Sure. Let's talk, yeah, definitely. Eric, do you want to come here?
So there was a slide about a potential capacity API that would allow users to see available capacity that can be spun out. And then there was also mentioning about ability for schedulers to reserve some capacity in the cluster. Would those two capacity somehow be represented in similar ways, or do you think those are completely separate representations?
It's a great question. I think it's still in the air. It's still unclear how much information about the potential capacity we will be even able to expose. So it might appear. It's still possible that it will not be regular Kubernetes API and objects and but instead some other more internal API. So it's pretty much it's pretty early in the discussion process. So I think that's the only the high level approach that we are still exploring. And
and then in the discussions, is there any value in representing the existing capacity of the cluster to the scheduler or in Kubernetes objects? So the capacity would reflect nodes and available hierarchy in the cluster that is existing.
I think I didn't fully follow.
I think nodes represent the capacity of the nodes. And then whatever we introduce in terms of groupings of nodes for topology, you can certainly have aggregated capacity up to a group of nodes or a group of groups. That should partially address what you're asking about. You'll be able to aggregate the capacity up a tree and see capacity at different levels.
So yes, so there will not be a standardized way, but people can derive existing capacity through those abstractions.
So the existing capacity we need to be able to derive anyway, no matter if we integrate with autoscaling or not. That is just needed for the scheduling, right? So.
Hey, thanks for the talk. I came in a little bit late, so apologies if you said this already. Just tell me to go and watch the video. Today I'm using Kueue plus JobSet with queue admission checks to basically get rough gang scheduling effect. And in this talk, you're giving us exact pod level gang scheduling, which is great. So my question is about JobSet, and if it's basically effectively replaced by pod groups with the gang scheduling semantics?
I wouldn't say
No.
that job set is replaced. You'll always keep using job set. Job set, we're working with that team and they're going to make workload underneath. So workload is now kind of a private message between savvy workload controllers and the scheduler.
Yeah, so scheduler will never like manage the whole life cycle of the job set and the jobs within the job set. So like, you still need a controller. It will just allow the job set to better integrate with scheduling and get the behavior that it wants at that level.
It's standardizing the current API between all controllers, and the scheduler is make a pod and hopefully do the right thing. And so we're making that interface between them a little bit more sophisticated, but it shouldn't affect the user's day-to-day experience.
Cool, thanks for the answer.
Although we could do cool stuff like kubectl list workloads, and if you have 9 different kinds of workloads, you could get them all in one list. I think that's kind of fun, but that's not our primary goal.
Awesome, thanks.
Hi. My question is, I'm curious, first, just like generally, how is this going to interact with draw? I don't know if you have the full answer to that yet, but
Yeah.
where are you going? And then to elaborate on that a little bit, is there going to be a way for drivers to indicate in that forest, like to indicate as the driver, this is the PCI structure or the NUMA structure, so that it doesn't have to be specified by the user, but it can just be populated by the driver, and then things will get scheduled in the right way.
All right. So I work closely with John Balamaric, and he kind of proxies to the WG device management. So I'll share a preview of our thinking, although this is not, there's still a lot of discussion. But the idea is that if a pod is request resources on a node, DRA initially started out as with resource claims only applying to nodes. And so that pattern works well. Now, you can also use DRA in theory, all this isn't fully played out, to like reserve multi-host resources like network fabrics. So if you have a layer above the pod called the pod group, you could, and that pod group, let's say, corresponds to an NVL72, then you could claim, the compute domain, or it's not how it works today, at the pod group level. You can have several replicas of those, and then maybe you have custom InfiniBand like on your site, and you have your own driver that manages your company's special InfiniBand. That could go at the workload level, and then that could like program, your custom network to like connect all these NVL72s. So the idea is that you've got 3 levels of hierarchy now, and you can make claims for drivers that own kind of like that slice of the hardware hierarchy. Now there's not enough metadata today kind of in DRA to like express the guarantees that the scheduler needs to sort of make sure there's nothing funky going on there. And you don't really want node selectors that like don't line up with your topology hierarchy. We're trying to figure out how to like kind of make that a little more of a clear path. So that's the current thinking. Does that help?
Yeah, and I was thinking specifically like PCI structure or NUMA nodes, which affect performance a lot, but like they tend to differ significantly between hardware, or even like just different versions of exactly the same top level SKU.
Yeah.
And
So-
if your driver could populate that metadata rather than needing to have the actual user like understand the PCI structure well enough to like.
Yeah, that topology graph didn't include within node, but definitely DRA drivers could provide information that's used to populate that hierarchy. And I would expect cloud providers would like have standard ones when you use their resources. So yeah.
Thank you.